Hi, in this video I'm going to go through A-level chemistry, OCR specification A, the 2019 paper, and this is paper 1. This is the second half of the paper. The first half I did in an earlier video. Okay, so here we have vanadium ions. Okay, and their common oxidation state shows them there. Complete the electronic configuration of the V3 plus ion. Well, let's look at the electronic configuration of vanadium first of all. So we look at the periodic table. There we've got 1s2 is filled up, 1s is filled up, 2s is filled up, 2p is filled up. Sorry, that's 2p6. 3s is filled up, 3s2. 3p is filled up, 3p6. And now we've got 4s2. So we've got 2 and 4s. And we've got 1, 2, 3 left in 3D. Okay, now the sometimes you can reverse the position of these, the 4s and the 3D. Now that's for the electronic configuration of the vanadium atom, but we want the V3 plus ion, so it's going to lose 3 electrons. So first of all it loses 2 from 4s, and then it will lose just 1 from 3D. So it's going to be, that is electronic configuration 3p6 3d1 for the V3 plus ion. Okay, now a student adds excess ion, Fe, to a solution containing the VO2 plus ions. Okay, so these are the blue ions, these ones, the +4 oxidation state. And observes the color of the solution changes from blue to green and then to violet. Okay, so we've got to explain that. Now, so the two half equations we're going to be interested in, well, we need this one here, the ion, and then we need this one here where the blue VO2 plus is reduced to the green V3 plus. Okay, how would we explain these observations? Okay, right, so if we look at those two, which is the most negative? Well, this most negative one is this one. So that means that's going to be best at pushing away electrons. So that's going to go backwards. Yeah. And this one is the most positive. So that's going to be the best at going forwards, taking in electrons. So that's going to go like that. So the ion is going to be reduced to Fe2 plus. And the vanadium is going, sorry, the ion is going to be oxidized to Fe2 plus. And the vanadium is going to be reduced to Fe3 plus. But that's not the end of the story, because if we look at this half equation here, we can see that that half equation is still more negative than the iron one. So as long as there's excess Fe, this one is going to be best to take. So that one is going to go forward, and it's going to, the V3 plus ions are going to be reduced to the V2 plus, and of course it tells us that they are violet. Okay, so how would you write that down? I think all you need to say there, if you look, they're quite happy with you saying that the, I would say that the electrode potential, first of all, for the VO2 plus V3 plus system is more positive than the electrode potential for the ion Fe2 plus Fe. That will give you to the green color change, and then also you can say that the electrode potential for the 3 plus 2 plus is also more positive than the electrode potential for the Fe2 plus Fe system. So that's going to move forwards as well. Okay. Right, construct an equation for the first color change from blue to green. So we are going to be interested in, I'll just rub this out here. We're going to be interested in these two half equations here that we've got. I'll get rid of that. Going to be interested in that one and in that one. Right, this one's going to go forwards. This one's going to go backwards. We need to balance the electrons, so we've got to multiply this one by 2. So you're going to have 2 VO2 plus, I won't bother putting the state symbols in, plus 4 protons, plus Fe ion goes to 2 V3 plus and 2 H2O and ion 2 plus ions. Everything in aqueous solution, of course, except for the ion. Okay. Right, here's a titration question then. So iron gluconate, which has got this formula, is experiment to determine the mass of Fe2 plus in one tablet. Okay, so right, the iron must be in the 2 plus oxidation state in the iron gluconate. The student crushes 2 tablets, right, and dissolves the powder in sulfuric acid. Okay, so you get 2 tablets in and that's made up to 250 in a volumetric flask. So we've got 2 tablets in there in 250 centimeters cubed. They take out 25 centimeters cubed of that, a tenth. That goes into the conical flask, and then that is titrated against manganate, purple manganate, who's in our burette, and that's going to be 0.002 mole per decimeter cubed, and they need 13.5 centimeters cubed of that. Okay, so we'll bear that in mind. Now the first question, it says, why is the student using 0.02, quite a low concentration of potassium manganate instead of the usual 10 times stronger? Well, look at the titer. There's obviously not very much iron in that. Okay, so then the titer is only 13.5. If they'd used the concentration 10 times higher, then the titer would have been 1.35. It would have been a tenth, wouldn't it? And that leads to a large percentage error. Because you're measuring such a small volume, you've got a large percentage error. So you need to use a more dilute solution of manganate to get a bigger titer. 1 mark, that's all you need to say there. Now the next question now is to use the student's results to determine the mass in milligrams of iron 2 gluconate in 1 tablet. Okay, so what we're going to do here is a 5 mark question this. Okay, so this is the manganate in the burette. So first of all, you need to work out the moles of manganate. Okay, so moles manganate. Moles manganate is going to be equal to concentration times volume. So that's 0.002 multiplied by 13.5, the titer. That volume's got to be in dm cubed, so that's over 1,000. And that gives us 2.7 times 10 to the minus 5 moles of manganate. Now look at in the instructions here, it says that 1 mole of manganate, in green, 1 mole of manganate reacts with 5 moles of iron 2. So therefore we're going to say moles of Fe2 plus in 25 centimeters cubed is going to be equal to that value multiplied by 5, and that gives us 1.35 times 10 to the minus 4 moles. Well, this is in 25 centimeters cubed. We want to find out how much we had in the whole of the thing that came from the 2 tablets. How much have we got in 250? So we're going to just multiply that by 10. So moles Fe2 plus in 250 centimeters cubed is equal to 1.35 times 10 to the minus 4 multiplied by 10, so times 10 to the minus 3. Okay, that came from 2 tablets. So how many moles of Fe2 plus have you got in 1 tablet? So obviously going to halve that. So moles Fe2 plus in 1 tablet is going to be that divided by 2, which gives us 6.74 times 10 to the minus 4 moles. Okay. Now, the question is asking, so we've got to find out the mass of iron 2 gluconate in one tablet. Okay, so if we look at the formula of iron gluconate, so the formula is C12 H22 FeO4. So 1 mole of iron gluconate contains 1 mole of Fe2 plus. Right, so that means then that the moles of iron gluconate is going to be the same. Now we need to work out the mass of iron gluconate. So the MR of iron gluconate, if you add up all of that lot together, it's pretty big, works out to be 445.8. So the final step now is you need to work out the mass of the gluconate. So that's equal to moles times MR. 6.74 times 10 to the minus 4 multiplied by 445.8, which is equal to exactly 0.30046 grams. Okay, now the asks us to work out in milligrams, and it asks us to give it 3 significant figures. So multiply that by 1,000 and you get 300.46 milligrams. But so 3 significant figures, that's 300 milligrams exactly. Now if you look in the mark scheme, it actually says 301 milligrams, but that is because they've kind of rounded up one of those answers midway through, and the true answer, I do believe, is 300 milligrams, not 301. Okay. Okay, and another question about iron supplements. Right, you've got 2 iron supplements. You've got iron 2 sulfate, and okay, and you've got 180 milligrams of iron compound in one tablet, and then you've got this other one, iron 2 fumarate, slightly larger mass of stuff there. Now, which one would provide the greater mass of iron per tablet? And I think you do need to work it out, because if you sort of guesstimate the MRs of these two, well, the iron is the heaviest thing, 55.8. They both got 4 oxygens in them. And so they're going to have roughly similar MRs. You can't tell one is definitely heavier than the other, and they've got roughly similar amounts of compounds. So you can't just, say, oh, that one's got a lot more compound with a smaller MR. So it's definitely more. We need to work them out. So let's do the first one, supplement A. Okay. So supplement A, we're going to do this. So the MR of iron sulfate is equal to, works out to be 151.9. Okay, so the percentage of iron in that is going to be, the iron is 55.8 by mass, over 151.9 times 100. So that one is 36.7% iron. So let's do the mass of iron in that tablet then. So the mass is equal to the percentage, 36.7 divided by 100, multiplied by the mass of the tablet in milligrams, 180. That gives us 66 milligrams in that one. And let's do the second tablet here. The same method, the MR of the iron fumarate is equal to 169.8. So the percentage of iron in that one is the mass of the iron over 169.8. That is equal to 32.8% iron. So the mass of iron in that one then is going to be 32.8 over 100 multiplied by the mass of the tablet, which is 210. And that works out to be 69 milligrams, slightly more than this one, which is 66. So the answer is B. That contains more. Right, here's a long question about making sulfuric acid. Okay, so, right. Sulfuric acid, first step is to manufacture SO2 from hydrogen sulfide. Explain why the enthalpy change for reaction 1 has a negative value, okay? And use the ideas about bond breaking and bond making, okay? So I think you need to say that the energy released on bond breaking, on bond making, is greater than the energy taken in when bonds are broken. Obviously, in any chemical reaction, you have to break some bonds and you have to make some new ones. And the energy you get out from making the new bonds is more than the energy you have to put in for breaking the old ones. So 1 mark, that's all you need to say. Okay. So now we, using calculations, explain whether reaction 1, which is this one up here, I've copied it in again, is feasible at 20 degrees C. Right, now they're giving us entropy values here. They give us an enthalpy value there. To determine if a reaction is feasible, of course, we need to use the Gibbs free energy. And if the Gibbs free energy is negative, then the reaction is feasible. And delta G, the Gibbs free energy, is equal to delta H minus the absolute temperature T delta S. Okay, so we know this value here, delta H, they give us there. But first of all, before we can work out delta G, we need to work out the entropy change, delta S. And let's just work out the absolute temperature there. Well, it's 20 degrees C. So 20 degrees C is equal to, add 273, it's 293 Kelvin. That's the value of temperature that we're going to use there. Let's work out the entropy delta S then. Okay, so, right, I will write the values in above this equation, I think. So how do we work out the entropy change? So delta S, we do the sum of the S of the products minus the sum of the entropy of the reactants. Let's do that in a different color. Okay, so let's do the reactants first of all. Well, we've got 3 lots of H2S, so that's going to be 3 times 206, which is 618 joules per mole. Don't forget it's in joules per mole, this, joules per Kelvin per mole. And we've got 3 lots of oxygen, so that's 615 for that. The reactants, well, we're going to have 2 SO2s, so that gives us 496, 2 times 248, that's 496, and 2 for water, that's 200, that's 140. Okay, so we add that lot up together, that comes to 636. Add these two together, they come to 1027. So delta S is going to be equal to the products, which is 636. A bit mad with the colors here. 636 minus the reactants, which is 1027. and that is equal to minus 391 joules per Kelvin per mole. Now, because this is measured in kilojoules, delta H is measured in kilojoules, we need to convert that delta S from joules into kilojoules before we put it into the delta G equation. It's a pretty common mistake to forget that, so that's minus 0.391 kilojoules per Kelvin per mole. Right, now put the numbers into the delta G expression. So delta G is going to be equal to minus 1,200, that's delta H, yeah, minus 293, the absolute temperature, minus times by minus 0.391. Okay, put all the numbers into that and you get a value of delta G equal to minus 1,104 kilojoules per mole. There's too many significant figures there, but all we need to say that quite clearly this is a negative sign. Right, so the reaction is feasible because delta G is pretty negative. Okay, so the reaction is feasible at 20 degrees C. Okay, now this is a bit of a tricky question. Calculate the standard enthalpy formation, okay, of hydrogen sulfide using the enthalpy change for reaction 1 and the standard enthalpy changes of combustion. So you may think, oh, it's confusing, which energy cycle do I use here? But don't forget the energy of combustion for sulfur is the same as delta HF for SO2. And likewise, the enthalpy of a combustion of H2 is actually the same as delta HF for H2O. And that's quite a common little trick they're trying to confuse you. So we've got to construct the Hess's law cycle here, and we're going to use a delta HF cycle. And okay, so I'll write that down. So we're going to have H2S, something in black. We're going to have 2 H2S plus 3 O2 goes to 2 SO2 and 2 waters. Right, we're using delta H formation. So the third thing we should have in our cycle here are the elements in the standard state. So I'm going to have sulfur, 2 of those, 3 H2, and I'm going to have 3 O2. Right, now which way are the arrows going to go? We're forming those things, so the arrows are going to go up. So I'll do that one in that green, and I'll do that one in blue, arrows going up. We know the value for delta H here, it tells us is that's minus 1125. Okay, now let's fill in the numbers on the arrows. So let's look at the blue arrow first of all. What we're doing there, we're forming 2 moles of sulfur dioxide. So we need 2 times that value there. 2 times minus 296.8. And we're also forming 2 moles of water, H2O. So we need 2 times that value, 2 times minus 285.8. So we add all that lot up together and we get minus 1165.2 kilojoules. Right, now this one, obviously the delta H of formation of oxygen is 0, element in its standard state. So all we've got to do here is we're forming 2 moles of H2S. So I'm going to call delta HF for H2S. I'm going to call that equal to X. So that's going to be 2X on that one there. Now we need to do our Hess's law thing. Okay, so we've got this number here, minus 1125. So we've got minus 1125. Now we're going against the arrow there. So we change the sign. So that's going to become minus 2x. We're going with the arrow there, so we stick with the sign there. That's 1165.2. Let's rearrange that to get x. So let's do 2x first of all. So you get 2x is equal to minus 40.2. So x is equal to minus 20.1. Now what is x? X is the enthalpy of formation of hydrogen sulfide, which is what we're going to find out. So delta HF for H2S is equal to minus 20.1 kilojoules per mole. You have to be careful with your signs there. It's quite easy to get plus 20.1 if you make a mistake. So you've got to be quite scrupulous about the way you, with your positive and negative signs. Okay. Right, now here's a question about equilibrium now. Okay, so in the second stage, we've got this equilibrium reaction, SO2 reacting with oxygen to form SO3. Okay, so it tells us we start off with so many of SO2, so much of oxygen. We had a catalyst. We know the pressure of the container. And when the equilibrium mixture is analyzed, it contains 0.35 of SO3. So we've got to write an expression for Kp. Let's do that first of all and then next bit, we're going to have to work out what Kp is. So Kp is going to be equal to the partial pressure of the products, which is SO3. And that's going to be squared because it's got 2 in front of it in the equation, divided by the partial products of the partial pressure of SO2, that's squared, multiplied by the partial pressure of oxygen, that's just to the power of 1. Okay, and include the units. Well, we're going to have, it's going to be 2 lots of atmosphere on the top. So that's going to be atmosphere squared on the top. And it's going to be atmosphere squared multiplied by atmosphere. So that's atmosphere cubed on the bottom. So that's going to be equal to ATM atmospheres to the minus 1. That's the units of Kp. Right, now we've got to determine the value of Kp. So before we do that, we need to work out the start moles of SO2 and the start moles of oxygen. All right, now how are we going to do that? Let's do the moles of SO2. Right, well, it says we fill up this container of that volume at RTP with SO2. So we can work out the number of moles by moles of SO2 is going to be the volume over the molar volume of the gas. The volume, it tells us, is 10.2, and the molar volume, of course, is 24 dm cubed. So that's equal to 0.425 moles. Let's now work out the moles of oxygen. How are we going to do that? Well, it says we put in some oxygen there. They put 12 grams of oxygen, okay, once the container has been filled with SO2. So we're going to do, we know the mass divided by the MR. Moles is equal to mass over MR. The mass is 12 grams. The MR of oxygen, 2 times 16, that's 32. And that is equal to 0.375 moles. And we're going to use these 2 values now in the next step. So what we're going to do is one of these start moles, final moles, and so on. Yeah. So I'm going to write down my equation, which is 2 SO2 reacting with 1 of oxygen to give us 2 moles of SO3. So here we're going to have start moles. Then we're going to have equilibrium. We're going to have moles used up. Then we're going to have equilibrium moles. Okay, so the start moles of SO2 we worked out over here was 0.425. Yeah, put that in. 0.425. And we've got 0.375 of oxygen. And we don't have any SO3, that's 0. And it tells us that equilibrium, we've got 0.350 moles of SO2. Okay, so that finally, so that's used up none of that. And 0.35 there. Now, right, if we make 0.35 moles of SO3, that means we must have used up 0.35 of that, because 2 moles of SO2 gives us 2 of SO3. So, and if we've used up that much of SO2, we've used half of that for oxygen. So that's half of that, which is 0.175. Now we need to subtract that from that, the used from the start to give us the moles at equilibrium. That gives us 0.075 for that one. This one gives us a 0.2 moles of that, and we know how many moles of that one we've got. Now we need to work out the mole fraction, so I'll write that down here. Mole fraction, which is of course is equal to the moles over the total moles. So we need to work out the total moles. Do it over here. Total moles of gas is going to be equal to that, plus that, plus that, which gives us 0.625 moles, okay? So now work out the mole fractions. So this is going to be 0.075 over 0.625. That's equal to 0.12. That's 0.2 over 0.625. That's 0.32 for oxygen. And that one, that's going to be 0.56. Okay, so now we're in a position to work out the mole fraction, the equilibrium pressure, the partial pressure of each of those. So the partial pressure is equal to the mole fraction multiplied by the total pressure. I'm going to call total fraction P there, and we're going to cancel some of them out, so I'm not actually going to work it out here. So that's going to be 0.12 big P total pressure, 0.32 P, and 0.56 P. Now we need to put those into the Kp expression, which we've worked out previously up here. I'll just cut and paste it. There's our expression for Kp. So there's a lot of working out in this. It is a 5 marker, but there's an awful lot of working out. Okay. There's our Kp expression. All right, got to put the numbers into that. Okay, so Kp, partial pressure of it, so that's that squared. I'm going to square the whole thing, so it's going to be 0.12 squared, and I have to square the P, don't forget, yeah. And that's, sorry, that's the wrong one because that's SO2, isn't it? Sorry. It's going to be this, okay. So just to sort of make it clear, 0.5, that's what we're going to have to do, and that's equal to 0.56 squared P squared, don't forget to do that. So that's going to be 0.56 squared P squared divided by this one squared, so that's 0.12 squared, capital P squared, multiplied by the partial pressure of oxygen, which is 0.32 P. Right, we can cancel out that P squared and that P squared, makes it a bit easier. So Kp is going to be equal to 0.56 squared over 0.12 squared multiplied by 0.32, and the total pressure, it says, was 2.5 atmospheres, so that's times 2.5. Put those numbers into the calculator, we get a value of 27.2 to 3 significant figures, and the units, as we said before, are atmospheres to the -1. So a lot of working out for 5 marks. Quite a lot of scope for making little mistakes, which will give you the wrong answer, but you will get error carried forward. Okay, right. The chemist repeats the experiment B at a different temperature and finds that the value of Kp is greater. We've got to say whether this temperature is higher or lower. Right. So I've pasted this bit here. This is important. This is an exothermic reaction, okay, in the forward direction. So Le Chatelier tells us, all right, let's just wait first of all. If Kp is greater, okay, then that means we've got more of that, we've got more products, and we've got less of that. Okay, so we've got more of SO3. Now, Le Chatelier tells us because this is exothermic, in order to make the equilibrium move to the right, we need to decrease the temperature to push the equilibrium to the right. So the second temperature is lower than 1000 Kelvin. It's lower. Okay. Right. Explain the significance of the expression that Kp is a lot bigger than 1. Right. If Kp is a lot bigger than 1, it means that you've got a lot more product. Okay. You've got a lot more product than you have reactant. So we can say that the reaction it doesn't go to completion exactly, but you get a lot more product than reactant. Okay. Right. The vanadium 5 oxide using the catalyst is a catalyst in equilibrium. Explain how the vanadium 5 oxide here increases the rate of reaction. Include a label sketch of the Boltzmann distribution on the grid below. Okay, and how many marks? This is 4 marks, I think. So we've got to label the axis. Probably get 1 mark for labeling the axis correctly. So on this one, we want energy. On this axis, we want number of particles. And the Boltzmann curve looks something like this. Okay, so it's skewed to the right. Now, we need to write down this is energy here. So this will be the activation energy without a catalyst. The area under the curve is proportional to the number of molecules. Okay, so the area, that blue area, is proportional to the number of molecules with energy greater than the activation energy. So in other words, they're the ones that can react when they collide. Right, if you use a catalyst, you're going to lower EA. It lowers, gives an alternative route to give a lower value of EA. So now the molecules which can react is all that lot there, okay, in the green area. So you can see the proportion of molecules which have energy greater than the activation energy is greater. So that means more collisions are effective and the reaction will occur more quickly. Right, okay, explain whether it's acting as a homogeneous or a heterogeneous catalyst. Well, if we look here, this is a solid, vanadium 5 oxide is a solid, and all the reactants and products are all gases, so they're in a different phase, so it is going to be heterogeneous. Right, on to weak acids now. Okay, the Ka 3 acids, weak acids is shown. Calculate the pH of propanoic acid of this concentration. Okay, so how are we going to do that? Well, I like to write down this propanoic acid. I'm going to write down as HA, and it's going to dissociate into A minus, its conjugate base, and into H plus. Right, I'm going to go with the start concentration. I'm going to write down the equilibrium concentration. Now, the start concentration is just that moment when you put the propanoic acid in before any of it has a chance to ionize. So that's going to be 0.08, and that's going to be 0, and that's going to be 0. It's not going to be really 0, the H+, but because there's some in the water, but we can ignore that because it's very small compared to the amount that's going to be released by the acid. Right, let's say that a small proportion of that dissociates. So let's say that's 0.08 minus X. So that means the concentration is dropped by X. So that means the concentration of that is X, and the concentration of the H+ is also X. Now we need to write down the expression for Ka. Ka is H+ concentration times A- concentration over HA. Right, now the concentration of H+ is, and H+ concentration is equal to A- concentration, and that's equal to X, okay? So let's just call that H+ squared, H+ times A-, yeah, it's H+ squared. Now HA, the concentration of HA is really 0.08 minus X, but that's approximately equal to 0.08 because it's a weak acid. This value of X is going to be hardly any of it dissociates, a very small amount. It's going to be much smaller than 0.08, so it's okay to approximate that and say that's 0.08. And that's important for the later part of the question. We'll come to it actually, 0.08. Now we know the value of Ka, so we're just going to rearrange that to get H+. H+ concentration is equal to Ka, which is equal to 1.35 times 10 to the minus 5. Sorry, H+ squared, sorry, multiplied by Ha, which we said was 0.08. That is equal to 1.08 times 10 to the minus 6. Take the square root of that, so H+ concentration is equal to the square root of 1.08 times 10 to the minus 6. That's equal to 1.039 times 10 to the minus 3. So take the minus log of that to get pH, and that is equal to 2.98 2 decimal places. So the pH, that is the pH there, or propanoic acid of that concentration. Okay, now let's move on, and it says here, a student adds, right, he starts off, let's see what he starts off with. He starts off with 25 centimeters cubed of 0.08 propanoic acid, and he adds to that a total of 45 centimeters cubed of 0.1 molar NaOH. So he's adding quite a large excess of NaOH there. Now, we should realize here that the ratio of these reacting of, so it's 1 mole of propanoic reacts with 1 mole of NaOH. Okay, show by calculation that 20 centimeters cubed of NaOH are required. So let's first of all, let's do moles of propanoic in the flask is equal to times the volume. The concentration is 0.08. The volume, it said we had 25 centimeters cubed. So in dm3, that's 25 over 1,000. That is equal to 2 times 10 to the minus 3 moles. Okay, now how many moles of NaOH do we need to react with that? Well, we need the same moles. So moles of NaOH needed, because it's a 1-to-1 ratio. Moles of NaOH is equal to 2 times 10 to the minus 3. The concentration of the NaOH, they tell us, is 0.1 mole per decimeter cubed. And we have to work out what volume do we need. Well, volume is equal to the moles divided by the concentration. We've just rearranged that equation there. So the moles is 2 times 10 to the minus 3. The concentration is 0.1, which gives us 0.02 dm cubed. Convert to centimeters cubed times by 1,000. That's equal to 20 centimeters cubed. 20.0 centimeters cubed. So that's that bit done there. Right, now calculate the next part then is calculate the pH of the final solution. Okay, now this is quite tricky because we're going to add an excess of NaOH here. So the way I would do that is I write down the equation. I'd write down, here's the moles of propanoic acid. Let's call that HA, propanoic acid. And that's going to react with NaOH. I'll just write down OH minus, forget about the sodium. What's going to happen there is you are going to form the conjugate base, A minus, and you're going to form water. Right, I'm going to write down here the start moles of each of these and the final moles and the final concentration as well. Right, the start moles of HA is equal to the concentration times by the volume, which was 0.08 multiplied by 25 over 1,000. And we worked that out before. That's equal to 2 times 10 to the minus 3 moles. The start concentration of OH minus, well, the start moles of OH minus is concentration times volume. The concentration was 0.1, and the volume is 45 centimeters cubed. They're going to add all together, so that's 45 over 1,000. That's equal to 4.5 times 10 to the minus 3 moles of that. We haven't got any A minus, and we don't care about the water. We just ignore that. Right, final moles. Right, now the OH minus is in excess. We've got a lot more OH minus than H plus. So that's the HA, sorry. So all the HA is going to react. So we're going to final moles of that is going to be 0. We can approximate that, none left. How much OH minus is left over? Well, they react in a 1-to-1, so it's going to be 4.5 times 10 to the minus 3 minus this amount, 2 times 10 to the minus 3. That's equal to 2.5 times 10 to the minus 3 moles. Okay, now the final concentration, right, the final concentration, right, this is going to be equal to moles over volume. Okay, so the moles is 2.5 times 10 to the minus 3. Now the final volume is going to be, well, we started off with 25 centimeters cubed, and we added 45 of the NaOH, so that's going to be 70. 0.07 dm cubed, so that's over that. So that gives us a final concentration then of 0.0357. So this is the OH minus concentration, don't forget, which is 0.0357. Now, how can we work out the pH from the hydroxide ion concentration? We've got to use our Kw expression. So we'll do this down here. Right, Kw is equal to 1.0 times 10 to the minus 14 from the data book, and we know that it's equal to the concentration of H plus times OH minus. So H plus concentration then is going to be equal to Kw over the OH minus concentration. Put the numbers in, 1 times 10 to the minus 14 divided by 0.0357. That gives us 2.80 times 10 to the minus 13 moles per decimeter cubed. Then what we've got to do is take the negative log of that to give us the pH. So pH is equal to the minus log to the base 10 of the hydrogen ion concentration, 2.80 times 10 to the minus 13. And we should give it to 2 decimal places. That gives us 12.55. Again, there's quite a lot of work there for the for 4 marks that you get for that question. Okay. Right, next bit then, we have got on the axis below, sketch a pH curve for the pH changes in that titration we just talked about when you add 45 centimeters cubed of the NaOH to 25 of our propanoic acid of that concentration. Okay, so just I've written down, you don't have to actually use these strict values here, but okay, you look in the mark scheme. So the start pH should be about 2.8, so that means I should do that start pH there. Now the end point occurs at 20 centimeters cubed. Okay, so we want to have the endpoint at 20, so the vertical bit here. Now the endpoint for a weak acid like this against a strong base is above, it's higher than 7, so we should have that there. Now the half equivalence point is going to be 10 centimeters cubed, and of course the half equivalence point, the pH at the half equivalence point is equal to the pKa for this. We know the Ka, so the pK is 4.989, so we should have that there just about at about 5. So you've got a half equivalence point should be about there, and you should have a little inflection in the line, so something like that. Right, and it should really finish, the pH finishes at 12.13, so it shouldn't, 12.55, so I shouldn't have that line going quite as high as I've drawn it. So I will just, don't want that to be any higher than there at the end, so I'm going to draw something like that. Okay, now you probably don't need to be exact with those numbers I was, because it's only 3 marks, but I think you probably, the important bits are probably having the end point being slightly alkaline, you know, up there. So I didn't need to rub that out. The end point should be slightly alkaline, you know, not a pH 7. You want it finishing roughly there. You want this little inflection there, and a fairly straight line in that bit there going upwards. Okay, right, so that is that bit done. Now, the student considers using 4 indicators. Okay, now which one should he use for the titration? Well, he wants to use one where the color changes occurs in this steep point of the curve here. So that's between pH 8 and 10 or something. So I think we should definitely use the Cresol purple. That one is the right one to use. The other two are way too acidic. You know, they're going to be changing somewhere down here, which is no good before the endpoint, and the other one will be past the endpoint. Right, now the student repeats the experiment with 25 centimeters cubed of potassium, of HCN, and add a total of the same amount of NaOH. So he's got the same volume and the same concentration of HCN as he had of propanoic acid, and he used exactly the same base. But if we look, what the difference is going to be, HCN is a much weaker acid than propanoic acid, okay, way weaker. So that means, right, what we're going to say there, one similarity, well, the end point, because we're using the same concentrations of volume, the end point for both is at 20 centimeters cubed. For the difference, I would say the start pH of the cyanic of HCN is a lot higher than it would be for propanoic acid. And also you can say the half equivalence point is going to be a lot higher as well. It's going to be, for that one, it's going to be about pH 9 or something. Yeah? The pKa of that one, minus log of that number is about 9, right? So it's way higher, but you don't need to give 2, you just need to say 1. I think the start pH is the most obvious one, and the similarity of the endpoint are the same. Right, now this last question, I think I referred to this earlier, is, right, it's a 1 marker, it's quite hard. Right, it says the student calculates the pH of iodic acid, right? Now, if you look at the Ka of iodic acid, it's actually pretty big. It's a pretty big number. It is, what is it? It's times 10 to the minus 1. You look at the value of iodic acid there. It's 1.78 times 10 to the minus 1. Right, that is almost like a strong acid, whereas look, propanoic acid is way weaker than that. Okay, don't forget the bigger the value of the Ka, the more of the acid that dissociates. Okay, so if you think, yeah, K, and I'm giving a lot more background than you need to do to give the answer to the question here, but just so it's clear, Ka is equal to that. Okay, so the bigger the number on the top, the more it ionizes. This bit, the more it ionizes, the stronger the larger the value of Ka. And iodic acid is a pretty strong weak acid there. Right, now it says here, the student assumes that the equilibrium concentration of HI is the same as the initial concentration of H. Right, now why? He measures the pH and the value is different from the calculated pH value. Explain why the measured pH is different from the calculated pH. That's quite a hard question, and it's for 1 mark. The reason is this. Okay, before we said we had our weak acid, let's say we had the iodic acid, right, and it's going to dissociate to form the conjugate base and H plus. The start concentration, that's 0.08, and we're going to say 0 for that and 0 for that. Equilibrium concentration, well, this is going to go down by, say, x, so we say minus x, yeah, and that's going to be x, and that's going to be x. Now, in the question, we said that because this x is a pretty small number, okay, because it's a weak acid, 0.08 minus x is approximately equal to 0.08. Now, that is true of propanoic acid because that is a pretty weak acid. But because iodic acid is quite a strong acid, this value of x is actually significant. So that is not true. You're getting, because the concentration, it says here, of the HiO3 is the same as the initial concentration, but it's not the same. It's not 0.08. It's going to be a bit lower. So that means if you use that approximation, when you work out the pH, you're not going to get quite the right answer, because iodic acid is on the verge of not really being a weak acid. It's almost a strong acid. Quite a complicated answer for 1 mark. Okay. Right, the final question on this paper is a 6 marker to do with rate of reaction. Now, before I read the whole question, I'll just say, we'll give you a brief overview what it's asking. Right. We've got this reaction between propanone and bromine. Right, and it doesn't say there, but it's actually catalyzed by an acid catalyst. And what we've got to do is we've got to look at the data they give us, and we've got to determine the rate orders for each reactant. And we've got to determine the rate orders for propanone, for bromine, and also for H plus, because it must be a catalyst. It doesn't appear in the rate, it doesn't appear in the equation. And once we've determined the rate orders, then we've got to write a rate equation, and we've got to determine the value of the rate constant. Okay, so let's do that then. Right, now the first experiment is going to give us the rate order with respect to bromine. Now if you look at this, during the reaction, as time proceeds, the rate of bromine, the concentration of bromine drops. Now you can see that's a straight line, so that means, right, the rate of reaction is constant, even though the concentration of bromine must be dropping. So therefore we can say that the rate is independent of Br2 concentration. In other words, it's 0 order with respect to Br2. So whenever you see a graph like that, and you've got a straight line there, concentrate, it means it must be zero order. Most reactions, if you looked at how one of the reactant concentrations drops with time, most reactions, they go like that, don't they? It's fast at first and then it slows down. And it slows down usually because the rate is dependent on the concentration of a reactant. In this case, it's not, so you just get a nice steady line. If you look, yes, constant gradient, rate doesn't change as bromine concentration changes. So zero order with respect to bromine, the first one tells us. Okay, now this tells us what's happening with the propanone, this one here. Right, the propanone concentration is on the bottom here. So this is not put in time. You have to be careful reading the axes here. So we've got how does rate change as concentration changes? And we've got a straight line through the origin there. So it's directly proportional. So that means rate is directly proportional to the propanone concentration. In other words, it's propanone to the power of 1. That is first order with respect to propanone. Okay, so we know 2 of the reactants. The final one now is the hydrogen, which is a catalyst. Okay, so here in these experiments, they're keeping the concentration of bromine and of concentration of propanone the same in experiment 1 and 2. But here you can see they have doubled the hydrogen ion concentration from 0.2 to 0.4. And what's happened to the rate? Well, the rate doubles. So that means that the rate is also directly proportional to the hydrogen ion concentration, or if you like, hydrogen to the power of 1. So it's first order with respect to that. Okay, so that's our sort of non-numerical bit of the question. Now we have to work out the value of, we have to write down the rate equation and work out the rate constant. So we know that rate is equal to Br2 to the power of 0, and of course that's equal to 1, so we can just leave, we don't normally put that in, leave that out. So I should put the rate constant in there. Right, it's the propanone to the power of 1 and H plus to the power of 1. Okay, so we rearrange that to get the value of K. So therefore K is equal to the rate divided by the concentration of propanone multiplied by the concentration of H plus. So now what we've got to do is put in numbers there. So we can use either experiment 1 or 2. I'm going to use experiment 1. So the rate constant is equal to the rate, which is 1.25 times 10 to the minus 5. Don't forget that up there. Mole per decimeter cubed per second. The concentration of propanone is 1.6 to the power of 1. And the concentration of H plus is 0.2. So work out the value for that, and we get 3.91 times 10 to the minus 5. Now we do need to work out the units of that. Okay, what's the units of the rate constant? Well, right, let's just do it here. Well, the units of rate of reaction is always moles per decimeter cubed per second. And that's going to be the concentration of propanone, that's moles per decimeter cubed. And of hydrogen, that's moles per decimeter cubed. So that's going to cancel out, that's going to cancel out. We get second to the minus 1 over mole dm to the minus 3. Bring it all onto one line, so the indices, then the sign of the indice changes. So that's second to the minus 1, mole to the minus 1, dm to the plus 3. So that's the value, and that they are the units of K. And that is the end of the paper.